All right, so here's what I want everybody to do. We're on number 5. And we are going to sketch these curves on our calculator. And then we're going to talk about the different shapes that we come up with. So the first one is r equals 2 cosine, r equals 2 cosine 3 theta. All right, so here's how this works. Go to your calculator to mode. And a few days ago, when we went to mode, we chose PAR because we were graphing parametrically, right? PAR, because we were graphing parametrically. Well, now we're going to pick POL because we are graphing in polar mode. So everybody find POL, highlight it. We're going to be graphing on polar mode. Now, make sure also you're in degrees. We can do this in radians, but I want everybody just to be in the same thing, so we're all looking at the same thing, same numbers. So everybody in degrees, right? Go to window. Theta min is 0. Theta max is, guess what? 360. Right? We're going to go once around. Theta step is 5. Your x mins and maxes and y mins and maxes, let's just make them, I'm going to look at my problems. Let's make them just -5 and 5. So for our x mins and maxes, y mins and maxes, -5 and 5. For the scales, just leave it at 1. So your x min, y min, -5, x max, y max, +5, and both of your scales are at 1. Okay? Now, press y equals, we're going to put in an equation. And this is the equation we're going to put in. So we're going to type 2 cosine 3 theta. Mrs. Ford, where's the theta? It's your variable button. Where we got x when we were putting in x, where we got t when we were putting in t's. Now when you press it, it comes up theta. That's your variable, your independent variable. Press graph.
Well, okay. I'm already gone.
What?
So what is your variable button? Same place you got x before. Just your x button.
Set second.
Why are you pressing second cosine? You're pressing 2 cosine 3 theta.
I was helping Blake.
Now what shape did you get? It's called a rose. You should have gotten a shape that looked like this. It's called a rose. There are 4 classical curves. We're going to hopefully get to all of them today. And the first one we're talking about is the rose. Now, I want you to make some observations about this rose. How many leaves does it have? 3. How long are those leaves? 2. This one you can easily tell because it's going out 2 units. These are a little harder to tell, but that one you can tell. It's 2 units. So for this particular curve, the length of the leaves is 2, and the number of leaves is 3. Right? Well, let's go to the next equation. R equals 4 cosine 2 theta. All right, leave everything the same and just type in the new equation. Jordan, just look on somebody else's. 4 cosine 2 theta. Okay? What is different? Well, this one has 4 leaves. And how long are they? They're 4 long. Again, it's easy to tell if you just count the hash marks on your axis. You set your scale at 1, so you can just count the hash marks, and they're 4 units long. All right. What about the next one?
Is the length always going to be the first number in the equation?
3 cosine 4 theta. Let's do the next one. The equation is 3 cosine 4 theta. So we want to know how many leaves there are and how long they are. We're trying to make some observations. So this one has 8 leaves, and they are 3 units long. And one more, 5 sine 5 theta. Give that one a shot. How many leaves and how long are they? Give that one a shot and let's see. What do we got? Okay, mode. You're supposed to be in polar mode. If you're not in polar mode, it's not going to work. That's the first thing I told you.
I just don't know what values I should set.
Okay, well, I shared this with the group, so ask a friend.
Wait, you can know? It's
Okay, how many leaves did this one have? 5. How long were they? 5. Now, we can do as many as we need to do, but we may have done enough. Can you make any observations about the equation
The first number is
and the length and number of leaves?
the first number is the length.
This number right here, Ferris says, gives me the length of the leaves. Does that pan out with all of our examples?
Yeah.
So if you had an equation, don't graph this one, R equals 16 sine 7 theta. You could tell me just by looking at it that the leaves are 16 long. The length, I should say, is 16. The length of the leaves is 16. All right. Now, what about the number of leaves? We know the length is this number right here. How about the number of leaves? What seems to be going on there?
What's some of them with the second number?
Well, for this one, there were 3 leaves, right?
The ones that are the same are like double.
Okay, so sometimes it's the same number, and sometimes it's double that number. What seems to be the trigger there that makes it one way or the other?
Odd or even.
Oh, so if that number is odd, like 3 or 5, there are that many leaves, right? But if that number, the theta number, is even, like 4 or 2, there are double that many leaves. So going back to this problem, which you're not graphing, you have told me that the leaves are going to be 16 long.
Yeah, 7 leaves.
How many of them will there be?
7.
7, because that's an odd number. Okay, so we're going to graph one, actually we're going to graph 2 more. Let's test out our hypothesis. So we're going to graph R equals 5 cosine 7 theta. We're just going to go ahead and graph that. But before we do, what's the length of the leaves going to be? And how many are there going to be?
7.
That's our hypothesis. All right, let's graph it and see if you're right. This was your hypothesis, not mine. Were you right? You got 7 leaves, and they're 5 units long. Now, for some reason, all my examples just about were cosines. I did one sine. I want you to see that that doesn't make any difference. So take a good look at that picture that you just graphed, and then go back and change the cosine to a sine and see if it's still the same picture. Is it exactly the same? No. Does it have the same characteristics though? Are there still 7 leaves and are they still 5 long? Yes. What happened to the picture? It just rotated, right? It just rotated. The leaves are in a different position, but there's still 7 of them and they're still 5 units long. So the difference between a sine and a cosine, kids, is the difference that it's always been. Remember when we graphed sines in the rectangular plane and cosines in the rectangular plane? You remember the shapes were exactly the same? They just shifted? Well, in a circular system, the shapes are exactly the same, they just rotate. So whether that's a sine or a cosine doesn't matter in terms of the shape of the curve. All right, that's a rose. So we'll have at some point a quiz, and the quiz will say R equals 10 cosine 10 theta, and the question will be, how long are the leaves? And you will say 10. How many leaves are there? And you will say 20. Because when that number is even, it's doubled. Even times 2. Okay? All right, so what's next? Isn't this exciting? What's next? Now we're going to sketch a different kind of equation. R equals 2 minus 3 cosine theta. All right, don't change a thing, just put that equation in. Don't change anything. R equals 2 minus 3 cosine theta. Now this is not a rose. Would you agree with me?
Yeah.
It's a cool shape, but it clearly isn't. It doesn't have leaves and petals and stuff. This is a different shape. So I'm just going to make a little note here of what this guy looks like. Okay. Now I'm going to sketch C. All right, so this was A. Now I'm going to do C. Now, I want you to think about what I just told you. Does the fact that this is a sine change this, have anything to do with the shape of the curve?
Yes.
No, 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 no. Sines and cosines are going to have the same shape. It's just going to be their positioning is going to be different. Okay? So the fact that one of my problems was a sine and one was a cosine does not fundamentally affect the shape. Okay? I want you to graph this one though because there's a difference in it.
It's too big.
It's too big?
Yeah.
So we may have to make our window a little bigger. Let me see, 4 plus 4. No, yeah, sine, theta. Oh yeah, that's going to be too big. It goes off the curve. Do you see that? It goes off your picture. So let's go to our window. What does it look like was too small? No, not the scale. Leave the scale alone. Y max, I think. So set that at 10. Set Y max at 10 and graph. See if that helps a little bit.
Yeah.
Now, did we get sort of the same shape sort of the same shape. See how the thing is situated left and right here? It goes to the left, and this one goes up. That's a sine-cosine difference. Okay? But there's another difference that's significant. What is different about this second shape? It doesn't have a little circle inside of it. This one is called a cardioid. Because if you use your imagination, what does that look like? A heart. That looks like a heart. This, cardioids are part of this family. This family of curves that we're talking about, like we looked at rows before, they're called limacons. And you will remember what limacons look like because they look like lima beans. So a limacon has a lima bean shape. If your limacon has these two numbers matching, you will have what's called a cardioid. If these two numbers match, you'll have a cardioid. So notice that the question in number 6 says, is it a cardioid? I didn't need the graph. I can tell you right now, this one's not a cardioid. How do I know?
2 don't match.
2 and 3 are not the same number. So I can look at letter B and tell you, no, it's a limacon, but it is not a cardioid because, again, I have a 2 and a 3. Look at number D, or letter D. Is it a cardioid? Yes, because it has a 3 and a 3. And it doesn't matter if that's a minus or a plus in the problem. If those numbers match, it's a cardioid. Doesn't matter if it's a sine or a cosine. If those numbers match, it's a cardioid. Okay? All right. We're half done with our classical curves. We're doing great. Isn't this fun? So now we're going to number 7. And it says now we're going to sketch this one. Now just, let's go back to our window. And let's go ahead and go down and make that y max 5 again, just so we have more of a square set up. So we had to change our y max to get the cardioid graph. Change your y max back to 5, so everything's kind of even. And now we're going to graph this guy. Okay, well, you know what you're supposed to do, right? Aren't you supposed to type r equals, right, or x, y equals, and what is r? What's the problem?
Square.
Oh, How do you, what do you think? Yeah, we're going to have to square root it. And when we square root it, James, to make sure we get the whole picture, we're going to have to take the positive square root, and we're going to have to take the negative square root. Because we want to make sure we get the whole picture. Remember when you take the square root of something, like if I say what's the square root of 16, you say plus or minus 4. That's what's happening here. I'm taking the square root of both sides, so I'm going to get plus or minus. Your calculator should automatically put a parentheses here. You need it. I think it automatically comes up, so it's not an issue. It doesn't? Okay, we need to put it in. We hit square root. Mine does, and I have an old calculator. And then negative square root. Now there is a little bit of a quirk in the calculator, and I'm not exactly sure this happens with these. And I know it's fixable probably, but I don't know how to do it. It may look on your calculator like these aren't connected, but they are. This shape, this kind of equation with the r squared is a figure 8. This is a figure 8. Now this particular figure 8 is going this way. They can go all different ways. They can be up and down, they can be sideways, but this particular one is on the diagonal. this classical curve is known as a lemniscate. Mrs. Ford, how am I ever going to remember this? Mispronounce the word. This is a lemniscate, but mispronounce the word and say lemniscate figure 8. Lemniscate figure 8. So that's the mispronunciation of the word, but it might help you remember it. Limasan lima bean. Lemniscate figure 8. So anytime you got an equation like this, in this class, it's going to be a lemniscate. Now, remember, just like there are billions of equations you can graph with x's and y's, there are billions of equations you can graph with r's and thetas. We're looking at the main 4 curves, which are called the classical curves, the rose, the limasan, the lemniscate. We have one more to talk about. Let's graph our second lemniscate. R squared equals 16 cosine. Then I want to talk about these for a minute. R squared equals 16 cosine 2 theta. So go ahead and graph that one. I got this one drawn up here. And tell me what the differences are. What are the differences?
The words go together.
Okay, so let's talk about that. Let me get it typed in here first.
It's not done.
Now this one actually did connect for me. Did it connect for you? So you got this shape. All right, now, so one observation that you already made is it's situated differently. Instead of on the diagonal, it's horizontal. I've already told you why that is. Can somebody tell me? Why is that?
Instead of sine, it's cosine.
Exactly. The function determines its position. Okay? Shape is the same. There's another difference, though. It's kind of hard to tell from the way I've drawn it. But did you notice, how long are these leaves? Or these things? 4. These are 4. Any idea why those are 4? Remember, when you graphed it, you did this. So the square root of 16 is 4. Over here, these leaves, it was hard to tell, maybe impossible to tell, but these leaves would have been 3. And that's exactly like it was with the rows. Remember with your rows equations, the number in front told you how long they were. This tells you how long they are, but you got to remember your square rooting. So they're 4 in this case. Everybody okay with that?
No, actually, how do you tell something? You put in R2 or you put it on 1?
Well, yes, it's R1. And then square root. And then R2 will be the negative square root. Now, Bo, you might want to pause on that because we're going to do some major changing on our calculators now. Okay, everybody ready? We're going to do some major changing. We're going to leave in polar. Obviously, we're going to stay in polar. But I want you to go to mode, and I want you to set it in radians. We're going to talk about y in a minute, but just bear with me. Change your calculator to radians. Okay, so stop what you're doing.
Are we still in polar?
You're in polar. You're changing to radians. Okay? Now window. We're going to go, our theta min is going to be negative 10 pi. And actually type in the pi. Now as soon as you go down to the next level, it's going to change it to a decimal, and that's fine. But theta min is negative 10 pi. Theta max is positive 10 pi. Theta step is 0.1. equation is.
No.
X min is negative 100. X max is 100. Scale is 1. Y min, negative 100. Y max, positive 100. And the scale is left at 1. So again, we have changed into radian mode. Our theta min and max are negative 10 pi, positive 10 pi. And our x's and y's are negative 100 and positive 100. Now you're going to see why in a minute.
What's theta max again?
The equation that we are typing in, clear out the old equations. We're typing in one equation now, and it is simply 3 theta. So type in the equation 3 theta and press graph.
Oh dang. That's cool.
What do you?
Now, what you just graphed is a full spiral. Go back to window and make theta min 0, and you will see more of the classic spiral that you are used to seeing. So go back and make theta min 0. Theta min 0, leave everything else the same. And you saw a spiral, right? Now, can you count about how many times around that spiral went? 5. It actually went around 5 times. And that's because theta max was 10 pi. In radians, a revolution is 2 pi, right? So if I said we're going 10 pi, that would be 5 times around. If I wanted it to spin more, I could give it a higher number and it would spin more. Now, can anybody think, why did I change this to radians? Could I have done this in degrees? Yes, of course. But what would have changed if I had done
It
it?
would have been a spiral.
No, it still would have been a spiral.
It's not the value factor, it's just theta.
Okay, somebody said, how come my window is bigger? How come my plane is bigger? It's bigger because I said I'm going to let theta max be 10 pi. That's approximately 31. My equation is r equals 3 theta. So r was going to be 3 times 31, so almost 100. That's why I made it 100. If I did this in degrees, guys, how many degrees is 5 times around? 1800. So how big would that window have to be? Over 5,000, right? To accommodate 3 times 1800. So when I'm graphing spirals, I normally change it into radians just to keep the numbers a little bit smaller. Could I graph everything in radians? Sure. It's up to you. Now, I'm not going to have you graph a spiral without my coaching, without my being here to help you set it up. So you don't have to worry about that. I'm like, I don't get how you got those numbers. It's okay. We'll practice a little more. Hopefully it'll make sense. But I'm going to coach you through the spirals because they are harder. Okay, but we got one more to graph. So this spiral, and that's our 4th curve, is the spiral. So there are your 4 classical curves, guys. We have one more kind of spiral to graph. The spiral that you just graphed looks like this. That is called a spiral of Archimedes. Or an Archimedean spiral. Now we're gonna graph the other equation, but wait, before you do, you need to adjust your window, and again, I'm gonna coach you through this. Theta min is staying 0, theta max is staying 10 pi, which is 31.4. Theta step, I'm going to change. I'm going to change it to 0.01. I think. My x mins and x maxes, let's make x min negative 0.1, x max 0.1. Leave the scale at 1. Y min negative 0.1 and y max 0.1. I should have planned this out a little ahead of time. Let's hit graph and see what happens. Okay, it's still working. Sooner or later, a picture's gonna come on. I just don't know how long it's gonna take. Yeah, well, but I need it to be small because my window is so small. I can't have but I need a small window because I'm dividing. I may have made it too small then.
A little too small.
Let's just wait a minute. Look, I don't know why you're packing up. We have time. We can wait on this picture.
Yeah, Dad. What?
It is really thinking. Yep, that made it crash. No, I'm just trying to.
Don't touch me, Dad. Dad. What?
I believe it is me.
Oh, you know what happened? I forgot to put in. Oh, that's what happened. Oh my gosh, I forgot to change my equation. 3 divided by theta. Now let's see. There it goes. Okay, so here's what I want you to do. Get your calculators back out. You shouldn't have packed up. And you got to type in the right equation, which is 3 divided by theta. So this one was 3 theta. We're doing 3 divided by theta. So that's what I forgot to do. I forgot to change my equation. My window was fine, but I actually changed it. So now I got my step set at 0.1, and I got my x mins and maxes at 1, and the same with the y's at regular ones, negative 1 and 1. So go ahead and set it up like that. Type in the right equation. You need this equation, and hit graph and watch what happens.
Another circle.
Okay, but the difference is, when you graphed this one, it started here and came out. When you graph this one, it starts out here and comes in. It's still spiraling, but it's starting to spin in instead of spinning out. This is called a hyperbolic spiral. So even though I won't ask you to sketch one without me setting it up for you, you need to know the difference between the 2 basic families of spirals. You have the ones that start in, and then you have the ones that start out. Archimedean, hyperbolic. All right, I'll see you all on Friday.
Yes.